In this video, we will discuss properties of eigenvalues. In the first property, we will show that if lambda 1, lambda 2, lambda 3, lambda n are the eigenvalues of matrix A, then we will show that lambda 1 square, lambda 2 square, lambda 3 square, so on and so forth, lambda n square are the eigenvalues of matrix A square. To verify this, let us consider matrix A to be 4, 2, minus 2, minus 5, 3, 2, minus 2, 4, 1. In order to find eigenvalues of matrix A, first we will write its characteristic equation, which will be determinant 4 minus lambda 2 minus 2 minus 5 3 minus lambda 2 minus 2 4 1 minus lambda equals 0. After expanding this determinant and equating to 0, we will get a cubic polynomial equation lambda cube minus 8 lambda square plus 17 lambda minus 10 equals 0. In order to solve this cubic polynomial equation, we write lambda cube. We will split this minus 8 lambda square as minus lambda square minus 7 lambda square. Next, we will split this 17 lambda as 7 lambda plus 10 lambda and this minus 10 equals 0. Next, we will take lambda square common from these first two terms and write lambda minus 1. Next, we will write 7 lambda as the common factor from these two terms and write lambda minus 1 plus we write 10 as the common factor from these two terms and write lambda minus 1 equals 0. Next, we will take lambda minus 1 as a common factor from the three terms and write lambda minus 1 multiplied by lambda square minus 7 lambda plus 10 equals 0. Next, we write lambda minus 1 into, we will factorize this quadratic polynomial as lambda minus 2 into lambda minus 5 equals 0. So this gives us three eigenvalues 1, 2 and 5. We write A square as vector A 4, 2, minus 2 minus 5, 3, 2 minus 2, 4, 1 multiplied by same vector A 4, 2, minus 2 minus 5, 3, 2 minus 2, 4, 1. As we know, in matrix multiplication, we multiply the columns of the post factor by the corresponding rows of the prefactor and add these corresponding products and write the elements. So the first element of A square will be 10, the second element 6, third element minus 6, so on and so forth, and the following elements will be 7, 18, minus 30, 12 and 13. We have to find eigenvalues of matrix A square. So first we will write its characteristic equation, that will be 10 minus lambda 6 minus 6 minus 39, 7 minus lambda 18 minus 30, 12, 13 minus lambda. Determinant of this equals 0. After expansion of this determinant, we get a cubic polynomial equation lambda cube minus 30 lambda square plus 129 lambda minus 100 equals 0. Lambda cube, we will split this minus 30 lambda square as minus lambda square minus 29 lambda square plus we will split this 129 lambda as 29 lambda plus 100 lambda minus this 100 equals 0. We will take lambda square common from these two terms, lambda minus 1. We will take minus 29 lambda common from these two terms and write lambda minus 1, and we will take plus 100 common from these two terms and write lambda minus 1 equals 0. Next, we will take lambda minus 1 common from each of these terms and write lambda minus 1 into lambda square minus 29 lambda plus 100 equals 0, it will be lambda minus 1 into this quadratic polynomial can be factorized as lambda minus 4 into lambda minus 25 equals 0. So we have eigenvalues of matrix A square, which is this, as 1 from this bracket, 4 from this bracket, and 25 from this bracket, which is equal to the square of corresponding eigenvalues of matrix A, which we have found as 1, 2, and 5. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. There is another property. If lambda is an eigenvalue of a non-singular matrix A, then we have determinant of A upon lambda as the eigenvalue of adjoint of A, which follows a simple corollary that if lambda 1, lambda 2, lambda 3 are the eigenvalues of a 3 by 3 matrix A, then eigenvalues of adjoint of A will be determinant of A upon lambda 1, determinant of A upon lambda 2, determinant of A upon lambda 3. And since we have seen in another property of eigenvalues, determinant of A equals lambda 1 into lambda 2 into lambda 3, which follows that the eigenvalues of adjoint of A to be lambda 1 into lambda 2, lambda 2 into lambda 3, and lambda 3 into lambda 1. In order to prove this, we will write first eigenvalue of adjoint of A to be, in place of determinant of A, we will write lambda 1 into lambda 2 into lambda 3. So it will be lambda 1 into lambda 2 into lambda 3 upon this lambda 1. After cancelling this lambda 1, we get the eigenvalue to be lambda 2 into lambda 3. Similarly, on the same lines, we can find the remaining two eigenvalues of adjoint of A to be lambda 1 into lambda 2 and lambda 3 into lambda 1. In the next property, if matrix A 2 1 0 0 2 1 0 0 2 has eigenvalues lambda 1, lambda 2, lambda 3, then eigenvalues of matrix A inverse will be reciprocals of eigenvalues of matrix A, that is 1 by lambda 1, 1 by lambda 2, 1 by lambda 3. Let us first find out eigenvalues of matrix A. For that, we will write characteristic equation of matrix A. It will be determinant 2 minus lambda 1 0 0 2 minus lambda 1 0 0 2 minus lambda equals 0. Expanding this determinant, we get 2 minus lambda cube equals 0, which means the eigenvalues of matrix A will be equal, that is 2 2 2. Next, we have to find out matrix A inverse. For that, let us first evaluate determinant of matrix A. That will be 2 1 0 0 2 1 0 0 2. Determinant of this, it will be this 2 multiplied by 2 2s are 4 minus 0, that is 4, minus this 1 into 0 minus 0 0 plus 0, that will be 8. So determinant of matrix A is 8. Next, we have to find out the cofactor matrix of matrix A, and that cofactor matrix or matrix of cofactors of A will be 4 0 0 minus 2 4 0 1 minus 2. If you don't know how to find cofactor of a matrix, then you can refer my videos on matrices. The adjoint matrix will be adjoint A, that will be the transpose of the matrix of cofactors of A. So that will be 4 minus 2 1 0 4 minus 2 0 0 4. Now A inverse, as we know, will be equal to adjoint of A upon determinant of A. So that will be 1 by 8 into adjoint of A, which is 4 minus 2 1 0 4 minus 2 0 0 4, which will be, after dividing by 8, half minus 1 by 4 1 by 8 0 half minus 1 by 4 0 0 1 by 2. We will rewrite A inverse for finding its eigenvalues, which is half minus 1 by 4 1 by 8 0 half minus 1 by 4 0 0 half. First we will write characteristic equation of A inverse, that will be half minus lambda minus 1 by 4 1 by 8 0 half minus lambda minus 1 by 4 0 0 half minus lambda. Determinant of this equals 0. Expanding this determinant, we get half minus lambda whole cube equals 0. That gives us 3 repeated eigenvalues, half, half and half. And the eigenvalues of matrix A that we have found out earlier have been repeated eigenvalues 2, 2, 2, which clearly shows that the eigenvalues of matrix A inverse are reciprocals of the eigenvalues of matrix A. Let us solve one example. We have to find the eigenvalues of matrix A and also that of matrix A inverse, and we have to verify that eigenvalues of A inverse are equal to the reciprocals of eigenvalues of matrix A. Consider matrix A, which is 3 minus 3 4 2 minus 3 4 0 minus 1 1. Its characteristic equation will be 3 minus lambda minus 3 4 2 minus 3 minus lambda 4 0 minus 1 1 minus lambda equals 0. Expansion of the determinant works out to be lambda cube minus lambda square plus lambda minus 1 equals 0. This is a cubic polynomial which can be factorized as lambda square plus 1 into lambda minus 1 equals 0. For finding the factors of a cubic polynomial, please refer my previous videos. Lambda square plus 1 gives us values of lambda to be complex numbers I and minus I, whereas factor lambda minus 1 gives us value of lambda to be 1. So we have 3 eigenvalues, lambda equals I, minus I and 1. Next, let us find out determinant of matrix A, that will be from this matrix 3 into minus 3 plus 4 minus of this minus 3, that will be plus 3 into 2 minus 0, that will be 2 plus this 4 multiplied by minus 2 minus 0, that will be minus 2. This will work out to be 1. In order to find A inverse, we have to find matrix of cofactors, that will be 1 minus 2 minus 2 minus 1 3 3 0 minus 4 minus 3. You can refer my videos on matrices to find out how to find matrix of cofactors. And adjoint of this matrix A will be adjoint A equals the transpose of matrix of cofactors, that will be 1 minus 1 0 minus 2 3 minus 4 minus 2 3 minus 3. We will find A inverse by using the formula 1 upon determinant of A into adjoint of matrix A. That will be 1 upon 1, that is 1 into adjoint of A, which will be adjoint of A itself. So A inverse will be 1 minus 2 3 minus 4 minus 2 3 minus 3. Now we will rewrite A inverse, which is 1 minus 1 0 minus 2 3 minus 4 minus 2 3 minus 3. Now we will find out the eigenvalues of A inverse. For that we will write the characteristic equation of matrix A inverse, that will be 1 minus lambda minus 1 0 minus 2 3 minus lambda minus 4 minus 2 3 minus 3 minus lambda. Determinant of this equals 0. Expanding this determinant, we get the cubic polynomial lambda cube minus lambda square plus lambda minus 1 equals 0. So this can be factorized as taking lambda square common. This will be lambda minus 1 plus lambda minus 1 equals 0. Taking again this lambda minus 1 common, we write lambda minus 1 multiplied by lambda square plus 1 equals 0. Lambda square plus 1 equals 0 gives us two values of lambda, the complex numbers I and minus I, and this lambda minus 1 gives one value of lambda, that will be 1. The eigenvalues of A inverse will be I minus I and 1. If we take reciprocal of these eigenvalues, we get 1 upon I minus 1 upon I and 1 upon 1, that is 1. These eigenvalues can be simplified by multiplying numerator and denominator by I. So the first eigenvalue will become I upon I square, which is minus 1. Next, minus I upon I square minus 1 and 1 upon 1, that will be 1, which will finally be minus I and 1, which are the same eigenvalues of matrix A minus I and 1. So here it is proved that eigenvalues of matrix A equals eigenvalues of A inverse. There is another property. If lambda is an eigenvalue of a non-singular matrix A, then we have determinant of A upon lambda as the eigenvalue of adjoint of A, which follows a simple corollary that if lambda 1, lambda 2, lambda 3 are the eigenvalues of a 3 by 3 matrix A, then eigenvalues of adjoint of A will be determinant of A upon lambda 1, determinant of A upon lambda 2, determinant of A upon lambda 3. And since we have seen in another property of eigenvalues, determinant of A equals lambda 1 into lambda 2 into lambda 3, which follows that the eigenvalues of adjoint of A to be lambda 1 into lambda 2, lambda 2 into lambda 3, and lambda 3 into lambda 1. In order to prove this, we will write the first eigenvalue of adjoint of A to be in place of determinant of A. We will write lambda 1 into lambda 2 into lambda 3. So it will be lambda 1 into lambda 2 into lambda 3 upon this lambda 1 gives us, after cancelling this lambda 1, we get the eigenvalue to be lambda 2 into lambda 3, which is nothing but this eigenvalue. Similarly, on the same lines, we can find the remaining two eigenvalues of adjoint of A to be lambda 1 into lambda 2 and lambda 3 into lambda 1. In the next problem, we are given matrix A 1, 2, 3, 0, minus 2, 6, 0, 0, minus 3. We have to find eigenvalues of matrix A and also eigenvalues of matrix A inverse, A power 4, adjoint of A, and that of matrix A bar. We observe that A is an upper triangular matrix. Therefore, its diagonal elements will be its eigenvalues. So, the eigenvalues of matrix A will be the diagonal elements 1, minus 2, minus 3. We know that the eigenvalues of matrix A inverse are the reciprocals of the eigenvalues of matrix A. So, the eigenvalues of A inverse will be 1 by 1, minus 1 by 2, and minus 1 by 3. Next, the eigenvalues of matrix A power 4 will be lambda 1 power 4, lambda 2 power 4, and lambda 3 power 4. That will be fourth power of 1, which is 1, fourth power of minus 2, 16, and fourth power of minus 3, 81. Next, we will find out determinant of A, that will be product of these three eigenvalues, 1 multiplied by minus 2 multiplied by minus 3, that will be 6. Now the property that we have just learned is eigenvalues of adjoint of A equals determinant of A upon lambda 1, determinant of A upon lambda 2, determinant of A upon lambda 3, that is 6 upon this 1, 6 upon this minus 2, 6 upon this minus 3, that will be 6 minus 3 minus 2. And finally, the eigenvalues of A bar, that is transpose of matrix A, that will be 1 0 0 2 minus 2 0 3 6 minus 3, which is a lower triangular matrix. Therefore, its eigenvalues will be same as its diagonal elements 1 minus 2 minus 3. So, the eigenvalues of matrix A bar will be same as these eigenvalues 1 minus 2 minus 3. Now we will write the important properties of eigenvalues in a nutshell. If lambda is an eigenvalue of matrix A, then the eigenvalue of matrix A square is lambda square. Eigenvalue of matrix A power n is lambda power n. That of transpose of matrix A dash is lambda. Eigenvalue of matrix A inverse is 1 by lambda. Of matrix Ka, where K is a non-zero scalar, its eigenvalue will be K times lambda. Of identity matrix I, it is 1. Of Ki, where K is a non-zero scalar, is K. Eigenvalue of matrix adjoint of A is determinant of A upon lambda. If determinant of matrix A is 0, it means that matrix A is a singular matrix, and in this case at least one of the eigenvalues, that is lambda, is 0. Next is sum of the diagonal elements of matrix A, that is A11 plus A22 plus A33 plus so and so forth plus ANN, is sum of the eigenvalues of matrix A, that is lambda 1 plus lambda 2 plus lambda 3 plus so and so forth plus lambda n. And finally we have product of n eigenvalues lambda 1 into lambda 2 into lambda 3 into so and so forth into lambda n is equal to determinant of matrix A. By remembering these important properties of eigenvalues, we can solve different problems based on the eigenvalues. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel to get more videos of this type. Give your comments to make these videos better. You can suggest topics on which you want me to make videos. See you in the next video. Until then, keep watching Number Collage. Thank you.